Okay, so here you go. I can't remember which video this is. This is for class 12. I think it might be video 4. Maybe it's video 5. Anyway, it's an example from Frank White's Fluid Mechanics, example 622. I get a long radius. It says nozzle, but I went ahead and did it for a Venturi, I guess. So I don't know. I went ahead and just I didn't. I guess I didn't bother with doing an iteration. I guess you don't need to here. Well, I didn't bother with the iteration for the coefficient, discharge coefficient. I think I just went ahead and used 0.9653. I think maybe I want to recheck that at some point, but I went ahead and used that anyway. So I'm doing this for air, so we have to worry about compressible flow, or maybe perhaps for compressible flow. We do need to use ideal gas law when it's air to be able to get the density. So we're going from a 10 centimeter pipe down to a 6 centimeter throat, and the upstream pressure, so that's up here, is 200 kilopascals, and we have a temperature of 100 degrees Celsius. And we found out that the pressure drop is going to be 60 kilopascals across these ports. And we want to estimate the flow rate in cubic meters per second. I might also throw in there that we probably want to check for the compressibility issues and then maybe to address them. So that's actually my purpose here. So the area at 1, so we call that 1, and over here is 2. Onto the thing is going to be pi over 4, and should be, it's 10 centimeters, right? So that's like 0.1 meters. It always messes me up. I can't stand centimeters. 7.854 e minus 3 meters squared, and then the area at the throat is 0.06, right? That's right, yeah, because it's 6 centimeters. 2.827 e minus 3 meters squared. Okay. So we're going to use the ideal gas law, and we're going to probably have to look up some parameters for air, but the pressure right here is 100. So the ideal gas law, let's write that out, that the density is going to be P divided by RT. So it should be on the inlet right here, on this side over here. And so the pressure is 200 kilopascals, but remember that should be, let me do it this way. We'll write the kilopascals, but remember it needs to be absolute. So we're going to add 101 to it, 101.4 if we're going to be precise for atmospheric, right? Because we want absolute pressure, and this is almost certainly going to be gauge pressure. And we're going to multiply it by 1,000 because we need to have it in, when we look at the units here, did we look up the R units, the units onto this? I think they're going to be, I think it's a Newton meter per kilogram degree Kelvin, right? Anyway, so you need to be in newtons per meter squared. So just be aware of that you need to, make that by 1,000. And so this, I didn't write it down, but this is the gas constant, and those units, make sure they're compatible. And then also remember this, the other thing to remember, these have to be absolute and this has to be absolute. So we need to add 273 to the 100 degrees Celsius to be able to get it into Kelvin. And you can trust me, all those units are going to work out to 2.816. But it's an important thing to make sure the units work out, so just be aware of that. That should be kilograms per cubic meter. And I went ahead and used a curve for a Venturi. So Venturi. So I'm sure that my numbers came out differently than them. But I used a curve that was supplied that just based the discharge coefficient, this guy right here, on the beta. But we know that it's going to be a function of other things like velocity. Usually Reynolds number is what we usually do. But this one, I went ahead and used this number. So this is the numbers that I have. But we have to be certain that, we get the thing from the right source. So don't be like me, kids. So we might want to recheck this at some time. It's a little suspicious. But we have this flow rate that we're going to get. So we're going to use, remember this equation uses the area of the throat for this. And we have 2 times the delta P divided by the density and divided by 1 minus that beta fourthed. So we needed that beta anyway, which is 0.6. But this guy is based on that 0.6 from a curve that I think was actually, might have been out of this book. It's another different book. 0.9653. And we have our area up here, 2.827, E minus 3, and square root of 2 times the change in pressure, which is, remember, 60 kPa. But if we're going to keep our units correct, let's go to base units. So we go to 60,000 to get newtons per meter squared, divided by our 2.816. And by 1 minus 0.6, right here, raised to the 4th. And we get a flow rate of 0.6038. And that's kind of what this problem has asked for. Well, I think it's probably better to write for kilograms per second, because we're talking about air, and you know that it's still, we still have the compressibility issues with the mass. We know that this is going to be the mass flow through here. This density here is probably going to be a little bit different. We don't know what the temperature change is going to be through there. I think most of the time for a nozzle, we usually go for isothermal action across there, if I'm not mistaken. Or is it isentropic? I can't remember, but I should probably remember, but I don't. In any case, what we've established right here is that that's going to be the volumetric flow. So we're going to use the density. We most of the time we assume that the density is going to be constant because we're treating this like an incompressible flow, even though we know it's not going to be incompressible. So anyway, I'm going to take my 2.816 and multiply it by my 0.6038, and I'm going to get 1.700 kilograms per second. And I think that's probably, it just makes a little bit more sense to me, at least, that we'd be using a mass flow instead of a volume flow. When it comes to liquids, I think the volume flow is kind of more appropriate, especially when US units you could compare to gallons per minute, and that kind of gives you sort of a better, or you get, I guess in the SI you could go liters per second, liters per minute, liters per hour, whatever. You can kind of get a sense of how much it is, but it doesn't make nearly as much sense for volume flow, I think, for when it comes to gases. But we want to check for compressibility. So, what compressibility check? Compressibility, something like that. Spelled something like that. Well, we need the speed of sound. So for a gas, it's going to be K, the specific heat ratio, times the gas constant times temperature. So for air, that's pretty standard, 1.4. You could memorize it. Why not? You could get the R. We already used it up here, so we might want to check this too for the units working out. So I'll leave that up to you. And then once again, for the temperature, it needs to be Kelvin. So we get 100 plus 273. And that comes out to 387.1 meters per second. We might want to check what our velocities are going to be. The velocity that we really could probably want to care about is the velocity at 2, because that's going to be the higher of the two velocities. Do I need to check it for anything else? Maybe. I don't know. So let me go V2. Okay, the V2 is going to be that, the volumetric flow rate divided by the area at 2. So what do we say? 0.6038. And then the area is 2.827. So we're going to get 213.6. We already see that's pretty close right there. So we're going to get a Mach number of V over C of 213.6 divided by 387.1. So that Mach number is 0.552, which is greater than 0.3, therefore not incompressible. Right? So otherwise, that means compressible. Otherwise known as compressible. There's whole courses taught in compressible flow. It's a lot more, and I think I have it scheduled so that towards the end of the semester we're going to cover some introduction to compressible flow. There, from one of the books, they gave me an equation, and another one they gave me a graph. And so I'm going to go with the equation here to do like a little bit of a modification, right? So what you could do is sort of a correction factor if you use this. I think from White, though, we actually have a figure. So it's sort of like one of the messed up things. But here's the correction that we have, the equation, we have a correction. We take 1 minus the brace right here. We take 1 divided by the specific heat ratio, then 1 with the pressure ratio right here. And I'm not sure if this pressure ratio, honestly, maybe the pressure ratio was supposed to be, I'm going to check that. Well, it didn't, I don't know if it actually matters, because I tried to compare this equation to a graph, and it didn't match, which really bothered me. Still bothers me, don't know what to do about it. But I would guess this is probably the absolute pressure ratio. I mean, it would matter, right? Yeah, it would matter, I think, because you're going to add something to both and then divide them through. So that's not the same thing as dividing them with as a gauge pressure. So I would think absolute. So, but I think when I was graphing it, I just graphed it by ratio. I don't think I graphed it by individual, but I better check that. So anyway, at A2 over A1 squared, and then the closed brace. So I believe that's the equation that we have as this, like, I'm going to call it a compressibility correction factor, but they called it an expansion coefficient or something along those lines. But anyway, 1 minus 1 over 1.4. And once again, I'm not quite sure if I want to do absolute versus So I don't know what's the difference between that, right? So what I wrote down on my page was 140 divided by 200, right? So what is 140 divided by 200? So we get an absolute of 0.7, right? But it should actually be 140 and 101.4, and then 200 and 101.4, which you should be able to add in your head, but I didn't. And I get 0.8. So there's either a 0.7 or a 0.8. So it depends. So there's a difference, and you should probably use the absolute, I would think, because that's in general, that's the way to go for a lot of these things, especially the ideal gas law and the speed right there. These are all using absolute numbers. So I don't know. Anyway, my ratio right here is, because it's a ratio of areas and it's squared, we could also use the ratio of the betas, but now it would be fourthed, right? Right? Sure. Because the beta is like a ratio of diameters, therefore ratio of areas is squared, and then we squared it, so it'd be fourthed. I guess so. I think so. But anyway, we get 0.9024 for right here. And so that's what we would multiply by, according to the equation that we use for here. They put in a little thing in here. They also put in, we also technically do mass flow most of the time, because it's pointless to do a volumetric flow rate. So maybe the mass flow would be that 0.9024 times the 1.700. So 0.9024 and 1.7, right? So times. So maybe a better prediction of the mass flow would be this in terms of kilograms per second. Yeah. But wait a minute, what did I just do right there? I decided to use, there was one, this thing, I got this one from a figure, and we got a different value for that. I got like 0.8 from the figure. Let's take a look at that, because we're at the 15-minute mark, so we're almost done with this anyway. Let's see. And I'm going to be underneath my assignments, homework, and this was 6. I think I actually posted this. Let me come back to this. Did I go under notes? I think under notes, I think I might, yeah, I posted these curves so you can see them yourselves. Let's see. Did I post them up there? Yeah, they got the expansion factor right here, so you can see it yourself. They did not work out. And there, see, this is my P1. See, that's what but here's P2 versus P1, just as a ratio of the things. And you can see where they line up on the curve right here. I can't figure out, see, this is the equation that I have. And I can't make out, and here's my betas in here. My beta is fourthed, right? My beta is at 0.5. And I can't figure out why this curve isn't working out the right way. It's bothersome. Like you could see from what we had before, that P2 over P1, what did I say? One was 0.7, one was 0.8. So you also have your betas here for your nozzles and your Venturis. They're the same ones here. So we had like something like right up in there. So I don't know. This 0.6. I'm not sure which one to use, to tell you the truth. But I'll figure it out at some point and get back to you. I don't know. I won't spend hours and hours on it though. It must be something to do with some signs. I must mess up some signs somewhere. It must be some kind of thing that's incorrect, and I just can't see it. And must be blinded. But anyway, that's the end of the video, and I hope this was helpful. I kind of posted it a little bit late, but maybe it's like a Friday and the homework is due on Monday. I think it might be helpful still. So have a great weekend.